Hello everyone. Today I'm gonna talk about the paper mining literals in the medical knowledge graph embedding for predicting companion animal diseases. This is the project that I and my lab member have been conducted last semester. Let's move on the content of today's presentation. First, I will introduce about the paper and the reason why we conducted this project. Second, I will explain about the graph construction. Third, this is the model architecture. The fourth one is the experiments, and the last one is the conclusions. Let's move on the introduction. In today's society, protecting health and improving the quality of life are important requirements. There are several biological similarities between the humans and the animals. For example, several animal diseases can be affected to the human, such as the skin disease or the stomach disease. As a result, uh, we can conduct the research on the animal first, and then we can extend to apply for the human. Also, companion animals are becoming familiar nowadays, and there are many people taking care of their pets. Moreover, the medical domain has been receiving more attention due to the importance and necessities of the healthcare today, and people want to recognize the disease risks uh, in their pets automatically and early. So our research focus on leveraging the data from the electric medical records to perform the practical tasks in the medicines. So in this paper, we propose the idea of learning representation of medical knowledge graph built from the electric medical record data of the companion animals by taking the advantage of the entity attributes. There are several approaches have been proposed to apply the graph embedding techniques in the medical domain. However, the information on the entity attributes had not been considered when using the techniques. So we in this project we aim to leverage the literal information in the entity to improve the performance of the model. And we also construct the medical knowledge graph from the electric medical record raw data, and we evaluate our model using these data sources in several strategies. Also, we summarize the experimental results and discuss the impact of literal resource extraction in the medical knowledge graph, and discuss about the future application direction. About the graph construction, we collected the electric medical records from the animal hospitals and then we construct the graph, and from the electric medical records we separate the data into the many entities or the nodes in the medical knowledge graph, and these entities are related to each other in different types of the relation, such as one-to-one, one-to-many, and many-to-many. And some nodes can carry the information or the attributes that are relevant to other nodes. And there are three groups of the nodes in our medical knowledge graph, separated by the literal attribute. The first group is the numeric literal. There are two nodes in this group. The first is the age and the weight, because the attribute of this node is the number such as the age and the weight. And the second group is the tactile literal, and we have the disease, symptom, drug, precision, the treatment, and the comments. This information is the text, and it can be relevant to the other nodes in the graph, such as the disease. It's been a disease in which a visitor's companion animal has been infected. So from the information of the disease, it can be similar to the other disease. This means two diseases are similar, will be close, will be similar, will be close in the graph. And the last group is do not contain the literal. To construct the graph, we call it the electric medical records from 31 companion animal hospitals, and the total of the medical records is around 86,000, and there are around 600,000 entities and 16 relation. And the medical information includes the age, gender, weight, the CC, it means the comment, the animal information, the disease, memo, the treatment, and the medicine. And we construct the center node. This is the diagnosis node. From this node, we can this is the representative node of the medical records, and to predict the disease, we can use this node, and we use the graph neural network to aggregate the information of all the medical information, and then we can predict the disease. Next, I will explain about model architecture, and we apply transfer learning with two paths. And in the free chain phase, we train the model to learn the relation among the nodes. And there is a fusion layer because this project we leverage the literal information, the numerical vector and the textual vector, and we use the gauge function to transform the entity embedding and literal vector into the same space to learn together. Look at the equation. We use the gauge mechanism and we transform the entity, numerical and textual vector into the same space to learn together. And in the free chain phase, we use GNN's irrigation combined with the attention mechanism to leverage the graph structure. It means from the center node, we can use GNN irrigation to capture all the subgraph. It means from the center node, we can capture the neighbor nodes information, and we use the GCN graph check and by interaction and the GAN combined with the attention ways. And in fine-tuning phase, we train the model to predict the disease in the medical records. So I will explain about the pre-trained model. And look at the figure. From the graph, we take the chip blast, this means the head, relation, and tail. And from the entity nodes, we take the entity embedding, the numerical and the textual vectors, and we push into the fusion layer. And after the fusion layer, we can receive the enriched embedding, enriched literal embedding, and then we push into the GNN's irrigation to leverage the graph structure. And in here we have n layers, and after each layer we can receive the outputs of each layer, and then in the last step we concatenate all the layers to get the final embedding. Then we use the scoring function to learn the relation between the head and the tail in the chipper. And in the scoring function, we transform the head, the final head embedding and final tail embedding into the relation space to calculate the score. And then to learn the embedding, we compare the negative chipper and the positive chipper. We generate the negative chippers, and we calculate the negative chipper score and compare with the positive chipper score to learn the embedding. In the fine-tuning phase, we train the pre-trained model to predict the missing disease in the medical record. And by using the GNN irrigation, the center node can capture the information of the subgraph. So we can predict the relation between the medical records and the missing disease note. So we use the PPR loss function and to compare the positive and the negative, and our goal is to predict the uh, disease information from the the coming medical records. And after calculate the score of the medical records and the disease, we normalize. We use min-max normalization to classify the link score of the center node of the record with all the diseases and define the correct diseases based on the ratio. This means if the score is greater than 0.5, we can determine this is the correct disease. And in experiment, we use several strategies to be able to evaluate the proposed model, and we compare the proposed model performance with the Bayes models related to medical knowledge graph and medical prediction. Also, we evaluate the effectiveness of using and not using the literal information in the model because our objective is to leverage the literal information in the medical knowledge graph, and we return the model by using and don't use the literal information to compare the efficiencies. And also we compare the effects of the of applying residual connection and the effect of the data sampling and hyperparameters. And we already conducted a series of the experiments to find the most suitable set of hyperparameters. So in the next step, we will evaluate the model by applying these approach strategies. In conclusion, in this paper, in this research, we construct the medical knowledge graph from the raw data uh, collected from the electric medical records, and we build a vision layer that can learn the literal information along with the entities in the model, and to increase the performance of the knowledge graph embedding, we leverage the information of the attributes by using the gaze mechanism, and we combine the knowledge graph embedding techniques with the graph neural network for maximum efficiency in animal disease diagnosis, and we turn the model into four types of aggregator, which is the GCN, graph change by interaction, and GIN to find the best model, the best aggregation in the medical knowledge graph. And we apply the transfer learning and build the two phases in the model, including the pre-training and fine-tuning. And we conduct a range of strategies to evaluate the performance of our model. And in the future, we can apply the model to other tasks such as the disease classification, and can also extend the study to human disease data. And as I mentioned in the introduction, uh, there are several similarities, but the biological similarities between the human and the animal. So beyond this research, we can attain uh, and conduct the other research related to the human disease to uh, attain and to apply for the human disease. So that's all my presentation today, and thank you for watching.